Hello, everyone. I think we can start. So good evening and good morning to everybody. Today we are happy to see participants from Europe and from across the Atlantic. I would like to welcome you to another Chisinau Connect.IT meetup. Today we will untangle quantum computing, its history and the future impact on global businesses and humanity at large. My name is Irina and I will be your host today. Before introducing our speaker, I would like to share some details about the platform we are using today. So Cisco WebEx is quite easy to navigate. In the bottom of the WebEx screen, you can see two important icons, chat and participants. I will give you a few seconds to check them out. In the chat section, you can write a question to our speaker. There you can see the drop down arrow. You can choose to whom to send the message. So when you do, please select to all participants options so we would not miss any questions. And also please address your questions in English. And if you click on the participants icon, you can see the host and the speaker list. However, you cannot see the attendees list as you can see only yourself. Please be aware that all attendees are muted by default in order to avoid multiple background noises. In case you want to ask any questions verbally, please send me a message to the host and I will unmute you for that time. To make sure that you stay updated with all upcoming events, join our Facebook page. I will drop the link in the chat section in a while. And now let me introduce you to our speaker. He has over 20 years of practical knowledge in the digital arena and extensive experience in product, business development, and user experience organizations. Prior to Endava, Justin was the founder and CEO of Nickelfish, a US-based digital agency which provided transformative digital services to the world's largest brands in finance, technology, and hospitality. Justin joined Endava family in 2015, and now as Chief Digital Officer at Endava, he's responsible for leading the global digital businesses, both from a client engagement and digital delivery capacity. Live from New Jersey, please welcome Justin Marcucci, Chief Digital Officer at Endava. Justin, all yours.
Irina, thank you very much. You can hear me okay?
Not very good, actually.
Okay. Is that any better? I can speak a little louder?
Is it possible to adjust a little bit the sound? I don't know what happened.
Sure, let's give it a shot.
Yes.
So this is real-time presenting, folks. This is how it works.
Yeah. This is how it works across the ocean.
All right, is that any better?
Not so much, it didn't change much.
Let's try that now. Is that any better?
A little bit, but don't go too far away from the computer.
All right, so we'll try one more option. Is that better?
Okay, so people are saying that the sound is fine, but I can hear from your side. Then, okay, let's go. In case there's gonna be any issues, I'm gonna wave you and we'll be good.
Okay. Got it. Let's share screen again.
Yes, please.
Okay.
All yours.
All right. So first of all, thank you very much. This is a first for me. I have yet to give a presentation at home, and so this will be interesting. And I'm sure there's one of a million things that can happen that will make this truly hilarious. The sound won't work, which we just experienced, so check that one off. My dogs could bark. My wife or my children could come in. A package could be delivered. It looks like they're going to rip up the driveway of the next door neighbor. So let's start this game of presentation mishap roulette, and we'll actually see what happens. Okay, so I'm Justin, as Irina said. Thank you so much. My responsibility at Endava is to work with our clients, and the organization at large works with our clients to have a better understanding of how they can utilize technology to achieve their business goals. So specifically how we can start to incorporate new ways of doing business, new technologies, solve new problems that make them more successful as an organization. And that's not just limited to technologies we are using today, but it's a part of that is understanding what kind of technologies are going to be coming down the road in the future that we're going to need to use. So enter quantum computing. Today I'm going to do my best to untangle quantum computing, which is a pretty complicated topic. And there's a lot of confusion in the market and in the world as to specifically how it will be used and what will happen when we achieve quantum computing. Now, make no mistakes, the implications of quantum computing on everything from technology to society to humanity will be massive. Now, just a quick disclaimer, for those of you that know me, I am not a quantum physicist. In fact, I'm not a physicist of any kind, for that matter. Hopefully there's no physicists dialed into the presentation, because I think that would probably be fairly embarrassing for myself. I'm going to be taking some really complex scientific theories and activities and simplifying them into something that's much more palatable, frankly, for as much for me as it is for you, because that's how I needed to learn them to understand them. Now, there'll be some questions at the end, and I definitely will answer at least 50% of those incorrectly based upon the complexity of the subject matter. However, take solace in the fact that across all of the infinite subset of universes that are out there, I will have answered every question correctly for you. Okay, so why don't we get started here? So the first thing is that Einstein, who we all know, once expressed his discomfort with quantum mechanics, and particularly the idea that it destroyed his long-standing thought process about how the universe worked in a very smooth and predictable and analog capacity. And he expressed that discomfort by saying God does not play dice with the universe, which is a very Einsteinian phrase to say. He had the ability to simplify things in a fairly amazing way. Now, Nobel-winning physicist Niels Bohr reportedly replied to Einstein's comment with, "Stop telling God what to do with his dice." And you know what that means, ladies and gentlemen, when you have two physicists of a same time taking conflicting positions on a topic, you're going to get yourself a good old-fashioned science fight. Now, Niels Bohr and Einstein wanted to come up with one theory to rule them all. Which one was correct? Einstein's structured and completely predictable view on how the universe worked, or Niels Bohr and his randomness and uncertainty that was postulated in all of the quantum mechanics and quantum theories that he's developed. Now, this debate went on for decades and decades, and Einstein was never comfortable with all of the implications of quantum mechanics. So ultimately, who won? Well, Niels Bohr won. Quantum mechanics has gone on to become the most successful and the most rigorously tested theory of all time. In fact, much of what has happened within science within the last 50 to 80 years has been involving quantum theory and quantum mechanics. Now, if there was any question as to the validity of the statements and the position that Niels Bohr and the other quantum physicists had, they were completely supported, and the nail was put in the coffin of Einstein's theories in 2011 when D-Wave released the first commercially available quantum theory, which would not be able to function, or that computer would not be able to function if, in fact, quantum mechanics and quantum physics was not correct. Okay, so what we're going to do is we're going to talk about the different areas of quantum computing today. We're going to talk about the science, we're going to talk through the application of quantum computing, and then again, we're going to talk what I think is just as important, if not more so, the impact that quantum computing will have on the world around us now and moving forward. Now, I have to talk about the science, and I have to go through that at some degree of detail, because otherwise, how quantum computers work won't make sense at all. So I will do my best, and I guarantee you, as we move away from science into the other ones, I will become entirely more credible. So to understand quantum computing, we need to first understand and talk through quantum physics. Now, quantum physics being the underlying science that makes quantum computing possible. Now, quantum physics is a fundamental theory in physics which describes nature at the smallest scales of energy levels of atoms and subatomic particles. Now, classical physics, Newtonian physics, and Einstein's theories of general and special relativity, they deal with the world at a macro scale. So everything that is human-sized and up, all the way through massive celestial bodies and galaxies and that sort of thing. Now, quantum physics deals with things at a microscopic or subatomic level, and it differs from classic physics in that there are limits to the precision at which we can measure and observe things in any kind of quantum state. Energy, momentum, space-time, angular momentum, all the qualities of a bound system are restricted to discrete values, meaning that there are limits, there's a quantization on the smallest unit of measure for all of those things. And objects within the quantum state can have both characteristics of particles as well as waves, which we'll get into. So in other words, if you're a subscriber or believe in Newtonian and Einstein's theories of relativity, both general and special, something like the moon makes a lot of sense. With enough information, we can use Newtonian physics to knowing where the moon is now, where it has been, to be able to thousands of years in the future predict with a shocking level of accuracy where the moon will be. And that's based upon those theories having a very smooth and predictable behavior and explaining how things work at a massive, massive scale. But if you were to zoom into the moon, I mean like really zoom into the smallest subatomic particles that make up its matter, what you would see is that they are erratic and unpredictable. And we have no confidence and incredibly low levels of precision to identify exactly what they are, what they're doing, and how they're getting on with things. And so that difference underlies the difference between quantum mechanics and general relativity, which frankly are incompatible as they stand today, these two governing theories of science. And much of the work over the last 50 to 80 years in science has been trying to normalize these two and come up with a theory of everything that makes quantum mechanics, the study of the incredibly small, and general relativity, the rules that govern the very large, work together. Now, things like string theory or loop quantum gravity are attempts at joining those together. But frankly, to date, we have yet to be able to find a theory that describes and allows these competing or conflicting theories to fit together in something that makes sense. So, okay, let's move on and start talking about quantum physics. Quantum physics actually was first postulated as possible in 1900 by Max Planck, as he suggested that radiation itself is quantized, their smallest units of measure. And that was then further compounded by Niels Bohr's atomic model that was released just before 1915. And Erwin Schrödinger, in 1926, he actually created a formula and an equation that helped to describe the behaviors of things within bound quantum systems. Now, that means that most of the thinking around the theory of quantum physics was established in the early 20th century, so almost 100 years ago, which is pretty remarkable. But it wasn't widely accepted as correct. And as late as 1935, Albert Einstein and all of his buddies that were really centered around relativity and the theories and the rules that govern Newtonian physics was incredibly uncomfortable and disagreed with the conclusions stemming from any kind of quantum behavior of particles. And particularly, he had problems with this notion of entanglement, which we'll get into in a little bit and describe what that is. Now, you don't need to understand all of those things, but you do have to start to think about what the world was like before and after quantum mechanics. Before quantum mechanics, the world was intuitive and predictable. Newton's laws and general relativity meant that if we had enough knowledge, the universe was actually fairly predictable in how it behaved. Space-time and energy were continuous. They were analog, and they varied smoothly from one region to another. And there was this notion of locality, which is pretty basic when you think about it, which is the location that an object is in or a particle is in takes on it's governed by its surroundings, and those surroundings influence the way that that object behaves. Now, after quantum physics, the world was uncertain and unpredictable. It permeated all of the rules and the way we thought about things at a small level, and rather than having exact ideas of how things worked, we started talking about things with this notion of probability, how probable things work. Things were quantized, again, space-time and energy, and all of the properties of matter had a smallest unit of measure and a shortest amount of time associated with how they could behave. And frankly, objects acted like waves and particles at the same time and just behaved incredibly weirdly. Now, I'm allowed to say things like weird when talking about quantum physics because, as I mentioned previously, that's correct. I am not a physicist. And so that is something that is totally okay. But now, don't take my word for it. Actually, look at some of the quotes from the fathers of quantum theory and quantum physics. Niels Bohr said, "Anyone who is shocked by quantum theory has not understood it." Richard Feynman, who is the father of quantum computing, said, "I think I can safely say that nobody understands quantum mechanics." Roger Penrose said, "Quantum mechanics makes absolutely no sense." Right? These are the people that developed the thinking and the theories that then have now been proven over the course of the last 80 to 100 years. There was actually an artist named Yves Tanguy, who in the 50s decided that the quantum realm, if you were, was so interesting that it became the sole inspiration for his work as a surrealist. Now, what's funny is the word quantum realm is not actually a word that was developed in science long ago. Marvel Comics developed the word quantum realm for the Avengers series, and it's actually started to become popular, which I think is pretty funny, where pop culture influences science. Okay, so there are three primary features of quantum mechanics that are most critical to understanding quantum computing: wave-particle duality and superposition, wave function collapse, and entanglement. And we're going to go through all three and hopefully make some sense of them. So wave-particle duality, this is the propensity for quantum objects to have properties of both particles and waves at the same time. So what does that mean? Let's use an example. Let's talk about an electron, right? A subatomic particle that spins around the nucleus of an atom incredibly fast, about 2,200 kilometers per second. Now, electrons have many properties. They can spin up, they can spin down. Their location is another property. Now, when we start talking about electrons in a sense of having certain properties and where they are, we have to start utilizing the Schrödinger equation to help determine the behaviors of those electrons. And using that equation, we can actually start to build some maps that illustrate where that electron is as it spins around the nucleus of an atom. Now, Schrödinger also created the Schrödinger dead cat theory and analogy, which has been incredibly popular, which we won't talk about in this, but actually highlights some of the duality of quantum physics in a really interesting way. Okay, so using the Schrödinger equation, let's look at this map. So this image represents the wave function of an electron's most probable position around a hydrogen atom. Right, so this is a map detailing probability. The brighter spots are where that electron is most likely to be, and the darker spots are where that electron is less likely to be, less probable to be. Now, what's actually incredibly interesting, this map of probability is called the wave function. So it's the wave function of an electron around a hydrogen atom. Now, that wave function is infinite. So an electron that's sitting in the palm of my, hydrogen atom that's sitting in the palm of my hand, its wave function for the electron extends all the way out to the edge of the visible universe, which means that there is a measurable, albeit incredibly small, likelihood that when we identify the location of that electron, it is on the other side of Saturn's rings, or somewhere even further than that, which I think is pretty remarkable. Now, wave-particle duality, the most bizarre part of a wave function is that it is more than the mathematical representation of probability. It actually manifests itself into the physical world. And when a position is unknown of an electron or going around an atom, that electron behaves like it actually is a wave, and it interacts with the world around it as a wave would. This is why we say that quantum objects have the features of both a wave and a particle, which this other visual here, this depicts a different way of looking at the highest probability of an electron's location. Now, before measurement, the electron's position is meaningless. It's not located at a single point when it's in a quantum state. Instead, it's actually in a state of superposition. And superposition means it's in all possible states simultaneously. So let's actually look at that definition, because this is very important. Superposition is the ability for a quantum particle to exist in all possible states simultaneously. Okay, so we've talked through wave-particle duality. how quantum objects can act like a wave and a particle at the same time. We've talked about superposition, where they can actually be in all states at the same time. Now let's talk about wave function collapse. Wave function collapse, this is the process that occurs when an unknown property of a particle is measured, and it collapses its superposition into a single defined state. All right, so this is, again, another map that shows where the electron is most likely located, and the higher points are where there's the highest probability for that electron to be located. Now let's take a look to actually find the electron. In doing so, it's going to cause that electron to abandon its state of superposition, and it'll collapse into a single defined position, aka this means we're collapsing the wave function. Now, it's probably worth noting that the probability of collapsing into a given state is known as the Born probability, which unfortunately is not the 5th straight-to-DVD version of Matt Damon's latest Born Supremacy film. However, okay, so let's go through this exercise. There it is. So by looking for the electron, we didn't actually find the electron. Instead, it collapsed from being in a state of superpositions of all locations at the same time into a single location. So observing the electron actually changed it, which begs the question, how did the electron know that we were looking at it? Well, remember, we're talking about things on a quantum scale, subatomic particles, the smallest known objects that make up the physical world around us. And in order to observe anything, some sort of information needs to be transferred from that object to whatever device is observing. And that transfer of information requires some sort of force to make it work. If we see something with our eyes or a microscope, photons are bouncing off of our eyes, that object, and then back into our eyes or the microscope. And when that photon, which is also a subatomic particle and is the smallest unit of light energy, when it interacts with the subatomic particle and that wave function of an electron, it collapses its wave function, just like that. Now, if we were to identify and use magnetism to try and identify the location of an electron, it would actually do the same thing. Magnetism's smallest unit of measure is also a photon. But in any case, by observing it, we have changed its state and collapsed its wave function, which is an incredibly important thing. In the quantum realm, observation is not passive. In the quantum realm, we cannot look and observe what's happening without fundamentally changing what's occurring in those locations. Now, incidentally, some interpretations of quantum mechanics do not require a wave function collapse. And in fact, the many world interpretation theorizes that there are nearly an infinite number of parallel universes, and each of those universes holds one of the possible quantum states of a particle that is in superposition. So that means that theory says that an object is intrinsically interacting with all versions of itself in all possible states simultaneously across parallel universes. Cool. This is the scale of incredulity sometimes that wraps some of the theories, and frankly the confidence and the intrepid nature of the individuals that came up with these theories is remarkable, because at face value they're saying absolutely ridiculous things. Okay, so let's talk about entanglement. Entanglement, I think, is one of the most complicated and certainly one of the most interesting of the 3 theories. Let's see, it looks like my clicker stopped working, so that's awesome. Okay, entanglement. This is the physical phenomenon which occurs when pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently from the state of the others. So that's pretty interesting. This thing just started working again. All right, so who had clicker dying in the home presentation mishap roulette? Because that's one that happened. All right, so let's unpack that a bit. So what does that mean, entanglement? So let's use electrons as an example. So electrons, as we talked about, can have a spin. They can spin either up or they can spin down. Now, until an electron spin is observed, its spin isn't known. And when it's not known, it's in a superposition and it's spinning both up and down at the same time. Now, it's possible to entangle 2 or groups of electrons. This means that when we take a look to determine the actual spin of an electron that is a part of an entangled pair or group, we're collapsing its wave function. And by collapsing the wave function of an entangled electron that's a part of a group, it instantaneously collapses the wave function of the other electron into the same spin. So it happens at the same exact time, and the same exact result is observed in both cases. Now, I think what's amazing is when I say instantaneously, we mean instantaneously. Entangled electrons can be moved to opposite ends of the universe, and their wave functions will collapse at exactly the same time. Now, that's a remarkable thing in and of itself. What we're saying is that entangled subatomic particles instantaneously and simultaneously change state together. Now, that synchronization seems to defy the laws of special relativity and the universal speed limit of the speed of light. But they actually don't. And the reality is we don't know why it happens. Right? There's something that is occurring, some information that potentially would be passed from electron to electron, but we don't frankly know what it is. We have no way to measure it. We don't know what that behavior ends up being. And so we can't say with any confidence what's actually happening. We do know, however, that we are able to identify and measure that those wave functions collapse simultaneously. Now, this non-locality really creeped out Einstein. This is the thing that he had the most issue with, because he thought it broke all of the rules of relativity in his understanding of the universe. And he called it spooky action at a distance. Now, again, I can use words like creepy when describing physics, because if you recall, I am not a physicist, and I'm actually closer to this hobbit than I am a physicist. Okay, so how does all this science actually relate to quantum computers? Well, frankly, quantum computing is computing that uses quantum mechanical phenomenon to actually be able to perform complex computations. Now, quantum computing in and of itself was first theorized in 1981 by Richard Feynman, and he came up with the first proposed model for a quantum computer. Now, about 19 years later, in the year 2000, the first working 7-qubit quantum computer was demonstrated. It was not working well, but it actually mapped to the model that Richard Feynman had created nearly 20 years later. And 11 years from there, in 2011, D-Wave actually made commercially available the first annealing-based system quantum computer. Now, that is within 30 years of the theorization of the model, we actually had something that was commercially available for people to start to utilize. And in 2018, Google announced the first 72-qubit universal gate quantum computer. And we'll get into really what that means. But basically what we're saying is within a 40-year window of time, quantum computing was theorized, was experimented, was tested, was commercially released, and is now starting to get closer to being perfected and usable on a larger scale. Now, you don't need to understand all of the different steps that happened within the world, but we can actually see what the world looked like before quantum computing with classical computing and what it looked like after quantum computing. So classical computing is bit-based. At the heart of classical computers are bits, transistors that can have the value of ones or zeros. Right? With very few exceptions, the result sets that come out of classical computing are exact. They're intended to provide an exact answer to the task to which they are provided. And the way that a classical computer goes through information is sequential. It actually looks at all of the different variables and all of the sequences and figures out a solution. And the more variables you add, the longer the computing time it takes to get to that answer. Now, with quantum computing, much inversely to regular bits, quantum computers have qubits or quantum bits. And qubits represent subatomic particles that can be in a superposition of both 1 and 0 at the same time. The answers that we get out of quantum computers are probabilistic. Because of the nature of quantum mechanics, it's all about probability. They're not exact. And so you get a lot of answers, and the more answers that we can generate, the better our sense of accuracy for the probability of an answer is correct. And lastly, quantum computers can solve certain types of problems instantaneously, or almost instantaneously, and things that would take classical computers eons to solve. Now, Seth Lloyd said a classical computation is like a solo voice, right? So one line of pure tones succeeding each other. Things are happening in sequence. A quantum computation is like a symphony with many lines of tone interfering with one another. Now, David Deutsch, who is the father of quantum computing in and of himself, said quantum computation is nothing less than a distinctly new way of harnessing nature. It'll be the first technology that allows useful tasks to be performed in collaboration between parallel universes. Tasks to be performed in collaboration between parallel universes. That is utterly mind-blowing, that we are thinking through the reality of parallel universes actually driving the science and the activity of objects that we can measure currently within our universe. And those sorts of things are why quantum computing is frankly so confusing and in some ways so controversial, because it brings up more decisions that need to be made and more conversations that traditionally would transcend that of general scientific conversations. So how do quantum computers actually work? Well, as mentioned earlier, quantum computers take advantage of some of the more bizarre features of quantum mechanics. While classical computers are bits, ones and zeros, quantum computers use qubits, again, which are bits that are in a superposition of 1 and 0 at the same time, and allows us to store and manipulate information in that way. Now, qubits themselves are made from quantum objects, and frankly, a lot of times they're electrons. And those properties are in superposition. So if an electron is used as a qubit, we're actually looking at its two different ways of spinning. And so its superposition is that it's spinning both up and down at the same time. Now, a basic computing problem involves figuring out the best way to combine a series of variables to determine an optimal solution set to a problem. And a classical computer has to go through every possible permutation of an answer and then determine whether it's good or bad, so what its fitness is. Now, for complex computations, and as we add more variables, that length of time and power needed to solve that solution increases exponentially. With quantum computers, using a series of entangled qubits, 2 or more, a quantum computer can actually explore the entire solution space, so all of the possible solutions to that problem instantaneously and at the same time. And as long as you have enough qubits, the addition of new variables doesn't require any additional time. Now, as it comes time to observe the answer to a problem, the solution space wave function is collapsed into a single solution with a high reasonably probability of fitness. And that's how we're able to map and do incredibly complex probabilistic calculations in instantaneous amounts of time using quantum computing. So voila, I hope that's incredibly clear, I'm sure. So yeah, that first part of this presentation is pretty exhausting. I know that to get through that actually requires a ton of focus and energy, more on your part than on mine. So thank you for bearing with me through that. But rest assured, we're actually through the hardest part. We're actually through the hardest part of this, and we're more than halfway done. Okay, so now we've talked through the science. Let's now talk about the application of quantum computing. So what can we do with quantum computing? Well, to really look at that, we have to understand how it's different from computing today. When the first computers were developed, they satisfied the needs that we had and the problems we needed to solve. As our problems have evolved, the kinds of classical computers we've developed have gotten more and more complex. As the problems that we needed and the computational difficulty of the things we needed to solve got larger, with classical computers, our answer was to just network a bunch of classical computers together to increase the amount of computational horsepower we had. But the underlying method by which those problems were solved has stayed the same throughout the history of classical computers, and they're simply things that classical computers cannot do that quantum computers can. Quantum computers are built to solve completely different kinds of problems that would take lifetimes, thousands of lifetimes for classical computers to do so. And it all comes down to the probabilistic calculations and the logic gates that are built on a parallel basis that allow quantum algorithms to take advantage of quantum computing. And it's those algorithms that are incredibly critical to making quantum computers successful. So let's actually look at an example. So figure 1, congratulations, you are getting married. Well done. With a marriage often comes a reception. And with a reception generally comes guests. And so for this wedding, there's going to be 10 guests that are going to be seated around a single round table. Now, naturally, because we are humans, not all of these guests like each other. So the challenge that we have to solve for is, how do you create the optimal seating arrangement around this round table for these 10 desks to have these 10 guests, to have as few pissed off people as possible at your wedding. So if we were to use classical computers to solve this problem, the classical computer has to go through every possible sequence of those 10 guests around the table, and that's going to take a decent amount of time. Now, a quantum computer can map that entire solution space simultaneously and come up with the best answer right off the bat. Now, if we're thinking about the math needed to determine how many possible permutations and sequences of a round table with 10 guests around it, we have to do something called factorial. And because there's 10 guests, it's 10 factorial is the math that sits behind that. And factorial of 10 is 10 times 9 times 8 times 7 times 6, so on and so forth, all the way down to 1. So for 10 people, the number of options sitting around a round table is 3.6 million variations of 10 people sitting around the table, which is remarkable, and it's a lot of number crunching for one 10-person wedding. Okay, figure two. Now, most people don't have a wedding with 10 people. Weddings have a tendency to be bigger events. And so for the case of this argument, we are going to say that there are 20 tables of 10 at this wedding. So there's 200 guests. And again, all 200 guests don't like each other. So how do we figure out the best possible configuration around the entire wedding to ensure we have the fewest pissed off people? Well, like the other one, the math here is factorial. It's 200 factorial because there's 200 possible variables within this equation. So let's actually do that math together. Okay, so 2, 0, 0, factorial, not a number. So yeah, my MacBook can't actually crunch 200 factorial because the number is so big. And so what we did is we went to the internet, and in doing so, we determined that 200 factorial is a number, but it's a number that has 375 discrete digits. A number that is 375 characters long. Just for a point of reference, that's a number that is larger than there are atoms in the known universe. So that's how big it is, and that's just for a 200-person wedding. So the kind of problem that you're solving, that quantum computing gives you the ability to solve, can be incredibly complex. Figure 3. So we've talked through a wedding, and something like 20 tables of 10 in a wedding, we can wrap our arms around. We can understand roughly that data set. But there's going to be things that we're going to need to start to use quantum computing to process that we won't be able to wrap our head around the scale of that data set. And a good example is climate modeling. Right? So the theory is that for advanced climate modeling, you would take the Earth and you would cut its atmosphere into billions of cubes, whether they're a meter big or a kilometer big. It would be cubes, and each of those cubes of atmosphere would have a handful of variables: temperature, humidity, barometric pressure, wind speed, wind direction. Now, what you then do if you had billions of cubes, each of which had several variables, we would then need to understand the interactions between all of those cubes together. And that would become trillions and trillions of micro interactions to understand specifically the relationship and the modeling necessary to accurately gauge what's happening from a climate standpoint. Quantum processing is absolutely required for something of that scale. We're talking about a scale of calculations that borders on incomprehensible at times. And some calculations, known as NP-complete, are so complex that a classical computer wouldn't even attempt to solve it. Some people have given classical computer problems that would really be better served with quantum algorithms, and it's come up with 14 billion years of processing time to reach an answer. But some of them just can't be done. So how does a quantum system even process these massive numbers? So there's really two ways to set up a quantum computer. The first model is called the annealing model. So the annealing model has less control over the quantum state, which has meant it has been easier to make progress with this kind of model to date thus far. It allows things to happen in a natural progression. So qubits in superposition are not manipulated nearly as much. And they're really allowed to kind of do their thing. Now, after that process runs its course and the answer emerges, we're in a position to actually see the benefits of an annealing model system. Now, it's easier to get qubits working together towards a solution in that annealing model because we're doing less manipulation of those objects in superposition. And as a result, annealing systems have more qubits associated with them, 1,000, 2,000. D-Wave continues to add to the scale of qubits in their annealing model systems. Now, there's also the gate model systems. Now, gate model quantum computers are much more difficult. They're trying to control and manipulate the quantum state of a number of particles in superposition over time and manipulate them in a much more serious way. Now, it's much harder, and that's due to the delicacy of quantum states. objects in superposition are very delicate, and their wave function can be collapsed by gravity, which stinks because we're all subject to gravity on some level, by sound, by light, by temperature. Most gate model computers have to operate at a fraction of a degree above absolute zero, so 0 Kelvin. And in doing so, that makes them very difficult to build and very expensive to manage. Now, there's just been some breakthroughs where there's actually hot qubits, which are able to operate at 1.5 degrees Kelvin, as opposed to fractions of a degree above absolute zero. But even those are very difficult. Now, gate model systems are far more difficult to get qubits working together in concert, and which is why they have a tendency to have like 10 to 50 or a little more than 50 qubits working together. Now, once a gate model system is created that's both efficient and stable enough to perform its own error correction, we're going to have the ability to start to run some real quantum algorithms in a way that are going to dramatically change the way that we think about things. So Shor's algorithm allows us to break cryptography by factoring large prime numbers incredibly fast, right? And so that will fundamentally mean that we have to reset the thinking on how cryptography and any sort of cryptographic science is based, because without having the complexity of brute force cracking prime number integers, well, that's something that we'll need to do. Now, additionally, Grover's algorithm will give us the ability to not have to perform linear searches through data. And so unstructured searches are far more rapid, and the more that we run them, the more accurate they will become. And so those two algorithms in and of themselves will change science and will change computing altogether. Now, when the potential ability of a quantum computer reaches a point where it can dependably and repeatedly run those sorts of quantum algorithms, we'll have achieved something called quantum supremacy. And quantum supremacy is when we can count on quantum computing being available at any time that we need to, and being the new basis for computation. Now, there's a lot of players in the market that are using quantum and are advancing quantum computers. Some of the established players like IBM, Microsoft, Google, and Intel are all focusing on gate model systems. They generally have a little more resource, and certainly they have a bigger charter to ensure that they can maintain the sort of competitive advantage over their competitors in the computing space. Now, some startups, D-Wave, Rigetti, Xanadu, they're using more annealing model systems, and they're building those sorts of platforms. IonQ is building a gate model system. Now, Google, again, released a 72-qubit computer in 2018, and late in 2019, they actually released a paper. In September of 2019, they released a paper very briefly that said they had achieved quantum supremacy. That paper was pulled down very quickly after it was put up there. Now, IBM, I think, has released a 53-qubit computer in 2020. Intel released a 49-qubit computer in 2019. And so they're all kind of hovering around that same area. But Google's the first one to have claimed that they have the ability and have achieved quantum supremacy. Now, just because we have quantum supremacy and we have quantum computers in the future doesn't mean that we'll change the way that we interact as the general public or as even technologists necessarily. Because we'll still use classical computing for the vast majority, if not all, of the computing needs that we have. And the way that we'll access quantum computers, because again, the build time and the expense and the stability of quantum computers mean that for the foreseeable future, there's not going to be one tucked away in the corner of your office. It means that big players, IBM, Google, Intel, Microsoft, are going to make quantum computing available in a cloud capacity. So much like you would buy bandwidth or processing power using AWS, you buy nanoseconds of quantum computing access to be able to run your quantum algorithms. And that's how most people and most organizations will use quantum computer, because of the prohibitive costs of actually building a quantum computer of your own. Okay, so we talked through the science, we talked through the application. Now let's talk through the impact of quantum computing and what that's going to have. So the introduction of this kind of technology, how does it alter the fabric of our reality? Well, new technologies are going to unlock new potential. We're going to learn in entirely new and different ways. So rather than the way science and frankly humanity has evolved to date, having a theory and then proving that theory over time with experimentation and data, we're also going to be able to flip that model of learning on its head and be able to look at massive amounts of data to develop answer sets and then build theories around why they make sense. And so it's a complete shift in the model by which we actually learn about things. We will solve problems that were previously unsolvable. And I'm not talking about that 1,500-piece puzzle that's been sitting on your kitchen counter the entire time we've been locked down, but things that fundamentally change our understanding of the natural world. Quantum computing, and I think where it gets really interesting, is how that as a technology starts to interact with other technologies, next gen in nature, that are starting to shape the future. So how quantum computing fuels artificial intelligence, robotics, nanotechnology, and genetics. And all of those things together are going to radically reshape the world in our lifetimes. Now, one of the things that we have to understand is that because so many different organizations, both commercial, corporations, as well as governments, are all trying to maintain and achieve quantum supremacy at the same time, they're not all going to do so in concert, right? So one day we're not going to go from having no quantum computing to having everybody have quantum computing. It's going to happen at different scales. And as it happens, and as we move from an academic mindset with quantum computing into something that is more competitive, commercial, and really has an advantage, we're going to start to see big sociological, socioeconomic gaps open up in the world economy, which are going to shift the balances of power and social control. And that's because an organization or a government that achieves quantum supremacy is going to want to protect that IP. They're going to want to protect that ability for as long as possible, because that's their competitive advantage in being able to achieve whatever agenda they're trying to achieve. But even in the meantime, we'll still have lots of other things going on, because quantum computing will absolutely be commercialized to a certain extent, because from a capitalist worldview market, looking at the way that the world will change means that there's an enormous amount of money and an enormous amount of things that can be created commercially that will be utilizing quantum computing. Life-saving medicines and drug discoveries, being able to understand and model the nuance of how pharmaceuticals both can be created as well as how they interact with the world, our physiology and the physiology of things around us. Climate prediction and farming advances. Now, we don't really yet understand the nuance of how the Earth's climate works and how it's impacted by all of the things that we do and all of the natural things that happen within the universe. And once we can accurately model those things, our ability to take advantage of the nuance of how to fix that climate, as well as take advantage of the biological nuance of how things grow within that climate, will mean that we'll completely rethink things like food production and farming. There'll be breakthroughs in chemistry and biology and materials. We'll be able, through the simulation of massive amounts of permutations of all of the known elements, we'll be able to come up with materials that are stronger than steel, or lighter than aluminum or carbon fiber. Things that actually include bioregenerative components that allow to have self-healing materials. There'll be rapid acceleration of artificial intelligence and machine learning, because those platforms and those technologies are built and improved based upon the amount of data it can use to refine those thinking models. And when we have something like quantum computing providing probabilistic calculations of enormous sizes, it will rapidly accelerate how quickly we can actually get to true artificial intelligence. But as well as the good things, there will potentially be some negatives. There'll be a destabilization of economic patterns as the world adjusts to potentially a new order of balance. There'll be widening of social and cultural inequity gaps based upon, again, who has quantum supremacy and how it's being used to build and further different parts of our society. There'll be an escalation of encryption and security challenges. Now, once quantum computing is something that is available for a small portion of the world, current cryptography theory goes out the window. And very quickly, those individuals responsible for creating cryptographic security are going to have to be using quantum computing in and of themselves to build models that prevent other quantum computers from breaking them. And so there's this escalation of the kinds of technologies and techniques we're going to use in those. And as well as there's going to be a weaponization of quantum systems. It doesn't actually mean weaponization in a world war stance, but they'll certainly be used to further the agendas of different governments and different portions of the world. Now, we are closer than ever to understanding the nature of the universe around us. But to understand the impossible may disprove the core belief systems of billions of people around the world. And as we gain insight into our biggest mystery and begin to see the fabric of our creation, religious dogma is going to be challenged and social schisms will absolutely emerge. If you think about the evolution of humanity in an anthropological sense, right? Thousands of years ago, the first versions of humans, when there was something that we didn't understand, we invented myth and legend and stories and religion to provide us comfort for the fact that we couldn't wrap our heads around why something was happening. As soon as we start to learn what exactly is happening in the universe that created those phenomena, the foundational pillars of a lot of humanity's belief systems are going to be knocked down. And it will create turbulence. Turbulence is all but guaranteed as we go through this process. But you have to remember that quantum computing, in and of itself, it has no agenda. Neither did the printing press, or the car, or the radio, or the television, or the internet. Quantum computing, like all technologies, it's a neutral entity. Humans, as we develop technology, we imprint our moral value upon it. We make the difference. And the consequences of what we create will always mirror our underlying qualities as humans. Now, some of those qualities that get mirrored have a tendency to mirror some of our more destructive traits, but not all of them. Some of them mirror our curiosity, and some of them actually show the depth of our compassion. We need to be aware that in radical times of change that we're in right now, the obligation to be a good person is more critical than it has ever been in the past. Both individually and as a species, our choices are going to have massive impacts on our world, society, humanity in general. And it's going to shape the future of everything around us in every conceivable dimension. So thank you very much. That is the presentation on quantum computing. Irina, I'm going to hand it back over to you. Oh, actually, before I do so, I just want to say, this is not my thinking alone. This presentation was created with the help and with the leadership of Jeremy Mays, of Seth Clifford, of Matt Cloak, and of Rob Machin. And collectively, all of us together pooled our thoughts and our knowledge to actually put in place what you just went through. So thank you to those gentlemen for contributing so greatly into this exercise. All right, Irina, so we're going to do Q&A now, correct?
Yes, first of all, I want to say thank you, Justin, for this comprehensive and very insightful presentation. Now, if any of you have any question, please drop them in the chat. First of all, we have a question from Valeria. I think there are two questions actually. And then we have some comments from Nikolai. Nick, do you want to unmute? Do you want me to unmute you, or you want to write something? Just let me know. Okay, so the first question from Valeria is, how many years will pass until quantum computing will become more common among people or institutions like universities? That's the first question.
So it's a great question. The answer is we don't know. I mean, as indicated, Google has already claimed in September of 2019, based upon their 72 qubit system, that they've already achieved quantum supremacy. And so, very frankly, Google could already be using quantum computing to advance their agenda from a technology standpoint or a research standpoint. Now, when it becomes more broadly consumable, I think that very realistically within the next 5 years, and this is my guess of just myself personally, within the next 5 years, we'll be in a position where most organizations can purchase quantum computing processing cycles via cloud systems. And I think it will likely be sold by Google and by IBM and those sorts of organizations.
All right, thank you. And the second question from Valeria Corina is, do programmers that are working in bits calculus have a future in this technology area?
Absolutely. So developers around the world, and certainly developers within Indaba, this is absolutely a place where we need to start investing and thinking about. Now because of how a quantum computer works, and we don't have access to one right now, it doesn't mean that we can't start to learn and get really skilled at writing quantum algorithms, right? Because you can write a quantum algorithm utilizing a classical computer. And there's companies and programs that allow you to access small bits of time using annealing gate systems to run those quantum algorithms. And so something that Matt Cloak, who's a part of Catalyst in my organization, he's actually set up a relationship with D-Wave, I believe it is, where you can actually utilize and start to learn about how quantum algorithms are written and how we would start to use them for our clients, for the things that we want to do. And so I think anybody that's interested in this doesn't have to be concerned about the hardware of quantum computing, but anybody that has a software-based mindset could definitely start learning about and practicing and developing their own quantum algorithms that will give them the ability to better get up to speed when we do gain access to quantum computing as an organization.
All right, thank you. All right, we have one participant that wants to be unmuted, so I'm gonna unmute you, Nikolai. Just one sec. Okay, Nick, hi, can you hear us?
I can hear you fine. Can you hear me?
Yes.
Yes.
Awesome. Yeah, so thank you for the nice presentation. You kind of got lucky with me because I'm an actual physicist, so
Awesome.
I don't know. I appreciate the presentation. It's good, and I mean, you presented a bunch of complicated concepts in a chewable way. So thank you for that. A thing that I'm gonna say though, it's Richard Feynman. He got a Nobel Prize. We should at least name him correctly.
Thank you so much.
But anyways, so with quantum computing, do you expect like a simple company that deals with not enormous amount of data like Google to actually need a quantum computer?
Well, and I think it all depends on how it's going to be used. You know, some of the first places that we've started to get requests as Endava for the use of quantum computing is in the insurance space, right? So some insurance companies, while they would never need to create a quantum computer, you know, the way that they do their risk profiling and risk modeling means that quantum computers will give them the ability to dramatically change the accuracy of their risk profiling, which will give them the ability to, frankly, change their business model and probably write policies that are going to require less payouts over time. And so a company like an insurance company, again, not necessarily a technology company, will fundamentally have the entire industry changed by quantum computing. And I think that, yes, I think that there will certainly be ways where we start to see quantum computing work its way into more normal courses of action. Airports, right? Anytime you're trying to simulate an incredibly complex environment, but even how to most efficiently operate and create process around how an airport functions on a day-to-day basis, given the variables of all the incoming flights and taxiing flights and baggage trucks and people walking around. Simulating those sorts of complex environments and modeling the most probable and best solutions for how to make them work more efficiently is something that quantum computing will absolutely have a hand in doing. And as a physicist, thank you for sitting through this presentation and dealing with probably what are a whole lot of slightly incorrectly phrased statements and mispronunciations.
No, that's fine. So another question, follow up, I guess, would be, so wouldn't it make more sense to move to a cloud-based platform in that case, given that you have so many difficulties in maintaining a quantum computer in the first place?
So I think that's exactly what's going to happen. And we've already started to see that that's what a lot of these large organizations are intimating is how they'll make their quantum computing available, right? So again, cloud-based AWS-esque systems where people are buying, you know, nanoseconds of quantum computational power to be able to perform their own quantum algorithms and see the results. So it'll definitely be cloud-based initially.
Oh, gotcha. Thank you.
Yep, thank you. Irina, do we have any more questions?
Yeah. Yes, actually, we got a lot of questions. I'm trying to figure them out. So we have a question from Oleg from Chisinau. He says, first of all, I wanted to say thank you for this presentation. That was really awesome, putting this amount of very complex information into this small presentation and still being able to make it really enjoyable. The question I have is on the actual data input that is required for the quantum computing. Basically, the quantum algorithm will shine processing large amount of data, but how would you actually input this amount of data for the quantum algorithm at to process it?
That's
going to be the same way we're going with the classic computing or another way? Thanks. So is it clear?
So I don't know if I entirely either understand the question, or if I do think I understand it, have the correct answer. But there's certainly some practicalities that are going to prevent and slow down the initial usage of quantum computing. Because as you indicated, the amount of data that would necessarily need to be loaded into a quantum algorithm or a database that quantum algorithm is accessing may be untenable for the classical computing system you're using to access that quantum computer. And so I don't know if I have the answer to how that would work. Again, I do encourage anybody that's interested in learning about that sort of thing to today start writing your own quantum algorithms and researching some of the available forums that you can use to validate the stability and the accuracy of your algorithm against some of the minor amounts of quantum computing we have available to us today. And because I think that it's only going to be through practice that we're going to start to understand how to most practically get around the kind of problem you just identified.
Okay, I hope, Oleg, that's right. If you need any other information, just let us know. All right, there are quite a lot of questions. Okay. We have a question from Iwan. How could we use quantum computing at Endava?
How can we use quantum computing at Endava? Right. So again, I think based upon the industries where we work, I think that we'll start to, as it becomes available to us, we'll start to be able to utilize quantum computing to build simulations and models for some of our clients' businesses. Again, I talked about the insurance space. So actually building systems and algorithms that will allow the underwriters at our insurance clients to better map and build out, probabilistic answer sets for how the kinds of policies that they write and the kind of risk they're willing to absorb is an immediate area where we are already starting to see interest. I think in some of the logistics space where we have clients, being able to simulate particularly how potentially a vessel is moving through the seas and simulate the climate that surrounds that vessel, simulates all the possible permutations of current and humidity, wave height, tides, taking all of that into consideration to build models that can create operational efficiency for the operation of those vessels is a place where we'll start to see quantum computing be realistically usable for us. And I think that there's a whole host of other areas as well. Certainly in the simulation of complex financial markets, I can see that our finance clients would be really interested in understanding what the probability of the behavior of certain businesses or industries and that sort of thing will actually have, because it will yield and drive their investment theses as they move through their day-to-day. So I think those are the areas where we'll start to see quantum computing be more useful and usable initially within Endava.
All right, thank you. There's another question from Martin. What is the first step to get into this?
What's the first step to get into quantum computing? Again, yes. I would recommend going, go to D-Wave. I think it's dwave.com, and sign up for what is, I think, initially a free trial of starting to use some of their tools, and just start to look at and read the papers and understand the best practices around quantum algorithm creation. That's a good first step, and certainly you're going to learn much more by using it and playing with it than you are going to be listening to somebody like me talk about it. And so I think that would be a really good place to start. And I think as an organization, as Endava, as we start to have more of a sense of how we believe we're going to utilize it, I'm sure you can look for detailed guidance and instruction from the likes of Owen, our Chief Technical Officer, as well as all of the senior technologists within the business that can help provide some guidance in this area.
All right, thank you. Another question from Razvan. Justin, what is your vision on how quantum computing will improve AI and machine learning?
Oh, that's a good question.
It's your vision.
My vision. Well, since I am not a data scientist or have dabbled in artificial intelligence personally, this is really going to be a guess. But again, based upon the way that I understand quantum computers will work and the kinds of probabilistic solution sets that they'll be able to provide, our ability to refine the neural networks and speed up and accelerate the learning events for machine learning based platforms will rapidly increase because we're going to be able to run so many additional simulations so quickly. So then rather than running it all sequentially with classical computers, being able to run all those simulations in tandem and do orders of magnitude more of them will mean that those machine learning based platforms will become effective from a learning standpoint substantially quicker as we go through the process.
Okay.
So I think I have time for about another 1 or 2 questions.
Yeah, we're about at the end of the list. Yeah, we have a question from Andres. Given that it seems that is most likely that the cloud-based services are going to be a sales model for many companies, do you foresee it will have an accessible cost, or it will be something that will remain exclusively to high-budgeted projects?
So using history as an example, I would assume the first accessible commercial models for quantum computing will be for high budget organizations. Certainly the cost of those systems, and you can even buy an annealing system from D-Wave, which is not a cloud interaction, but we're talking tens of millions of dollars here. And so I would assume, just to make sure and start to offset the R&D costs of the building of quantum computers, those first accessible interactions in cloud-based portals will be very expensive and will be limited to only the largest organizations in the world. Much like anything else, as those models start to offset that investment and as the systems themselves become more stable and the manufacturing of those systems becomes slightly more understood, the costs will come down and get to a point, much like how the cost of storage goes down dramatically over time. I think we'll start to see something like that, but I would anticipate they'll be pretty expensive up front.
All right, so we have 2 more questions and we're done. Yeah, a question from Paul. Okay, hello, I have one question for Justin, if the time allows. Yes, of course. Do you think that quantum computers will be able to prove or disprove that we live in a deterministic universe?
I think that I think that the likelihood of the impact of quantum computing completely shifting our understanding of the universe and obliterating the notion that it is a deterministic Einsteinian universe is very likely. I think that parts of that have already been put to bed based upon the success we've had with quantum computing to date as a technology community. So yeah, I think it's very likely that we will have to completely rewrite our knowledge of how the universe works once quantum computing gets to a point where we can use it to apply a lot of the questions that have inspired and challenged physicists and naturalists to date.
And we have a question from Daniel. He asks you, do you think that we live in a simulation?
It is certainly a theory that has a surprising amount of support. Do I think that we live in a simulation? I think it depends on what you would define a simulation as, right? So to me, a simulation is any system that is created to drive and measure a certain kind of behavior and what happens. And so a simulation, particularly a simulation that would have parallel universes, each running slightly different models, would be very possible that could happen. If you define a simulation as not necessarily a digital simulation, but a simulation being an environment that is set up to run a course of events. So this starts to get into some theological debates a bit, but depending upon an individual's appreciation for higher power or for God or for something like that, Now, you could actually make an argument that a God created this universe as a simulation, and all the universes running in parallel is a simulation. It doesn't mean that it's a digital simulation necessarily, but it could certainly be a simulation. But that's those sorts of theological questions and theological implications from questions that are derived from this debate around quantum computing are why it's such a controversial topic at times, because it does start to challenge all of the foundational knowledge that we've developed and grown on as humanity.
Someone says that, no, it's not a theory, it's Elon Musk's craziness. All right. So first of all, Justin, thank you for taking your time and making this presentation. Thank you for your patience. I want to thank you, thank all the participants for being with us until the end. And I would like to answer a question about the presentation. Yes, I think tomorrow we will drop a link in the Facebook event where you can watch the presentation if you want to rewatch it, just in case. Just stay tuned. Also, meanwhile, I think in a short time, you'll get an email to give us some feedback on the presentation and the organization. And if someone is interested in DevOps, on the 6th of August, we're going to have another presentation with another special guest on DevOps. So stay tuned on our Facebook page for more details about the event.
Right.
So thank you again, and see you soon, hopefully, maybe in Chisinau live. Yeah.
It's open. Everybody, thank you so much for sitting through that, and hope you have a wonderful day. Thanks for the opportunity to speak to you.
Yes, thank you. Bye.
Take care.
Bye-bye.